You've heard of blackouts, times when the power grid fails and lights go out. Or rolling blackouts, when sections of the grid are turned off at certain times to manage demand. But what happens when massive parts of the grid fail? Due to a catastrophic event or accident? Incorrectly set equipment? Like what happened in London in 2003? Or untimely coincidence, like the blackouts in 2019? I'll explore those events in another video, but when we lose big sections of the grid, it's really sensitive to turn back on, to manage that demand. So you can't just turn it back on any old way. That's why we have a black start procedure. Before we dig too deep, let's first get an understanding of inertia and synthetic inertia. Inertia is a system's resistance to changes in motion. Imagine you're driving a car. If you suddenly take your foot off the accelerator or hit the brakes, the car doesn't change speed instantly. It resists that change because of its mass. That's inertia. Now picture that car as a spinning turbine in a power station. If there's a sudden imbalance in the grid, like a generator failing or demand surging, that spinning turbine resists the change in frequency. Just like the car resists a sudden stop. That resistance buys time, seconds, for the rest of the grid to respond. Without that, the frequency would swing too fast, too far, and risk a blackout. The more mass we have, like the truck in this example, the more inertia we have and the longer we have to respond. So what makes synthetic inertia synthetic? Well, battery storage and solar have no moving parts, so no spin and mass to give it inertia. They produce DC power like most wind turbines do, which then needs to go through an inverter to become AC power. Some of these inverters operate in what's called grid following mode, where they need a stable grid frequency already present in order to export power. Whereas smarter inverters are what's called grid forming, which can operate in island mode, where they set their own frequency and voltage on their own like a microgrid. Grid forming means that instead of needing a live grid to latch onto, these generators can create their own stable 50Hz voltage and frequency, just like a traditional spinning turbine would. You can think of it like a train. You first need a locomotive, a generator, that can set the speed and direction for the whole grid. Without that engine, the carriages, or grid following devices like traditional wind and solar, can't move at all. Only once a stable reference exists can they latch on and follow the system. By some neat physics, traditional synchronous generation, or simply turbines, are naturally grid forming. This is because the turbine frequency is set by its speed, and the speed is controlled by the plant operators. Because of its spin and mass, it has inertia, so when the load changes, the inertia tries to resist the load change, keeping the system stable. So how does grid forming work? The inverters monitor the grid frequency using something called phased locked loops, or PLL for short. A PLL simply generates an output signal with the same phase and frequency as its input signal. This frequency can then inform a relay running RoCoF Protection, also known as rate of change of frequency, and in industry is often seen as a DF over DT relay. This protection is typically used to disconnect sensitive generators when frequency changes too fast, but can also be used in battery storage systems to inject power into the grid when frequency drops, or absorb power when frequency gets too high, adding stability. The power it puts in or takes out of the system is determined by the synchronous generator swing equation, which emulates a real synchronous generator's inertia. The swing equation looks like this, where we have m, which is our inertia constant, which for a synchronous machine is a physical property of 2x the stored kinetic energy, divided by the angular velocity, which is typically 2 pi 50 in the UK. This gives us the inertia constant in megawatts per hertz or seconds. Then we have the rate of change of frequency, which is delta omega over delta time, omega being the squiggly w, which in a synchronous machine is angular frequency, but in a power system is simply frequency. And finally we have PM, which is input power, and PE, which is output power. We can then rearrange this equation to find out what our rate of change of frequency is. So delta omega over delta time is equal to power in minus power out divided by our inertia constant, which simply put means our RoCoF depends on the difference between our power in and out divided by inertia. So if we have more power out than power in, our frequency falls, and if power in is greater than power out, our frequency rises. Changing our inertia, m, will dictate how quickly or slowly that frequency changes. Now we understand inertia, let's take a look at blackouts to really understand why black starts exist. We first need to understand how the grid is normally balanced and what happens when it isn't. The NESO, or National Energy System Operator, are responsible for managing and balancing the grid. What does that mean? Well, we have demand, which is the people and businesses connected to the grid who want power. And we have supply, which are the generators that provide that power. When we have too much supply, the grid frequency rises, and when we don't have enough supply, the frequency falls. In the UK, our frequency is set at 50 Hz, with a margin of 0.5 Hz either side, before the NESO must act to correct it. If it goes beyond that range, the NESO goes into alert, where it must use reserves to correct the frequency, and if it manages to go below 48.8 or above 51.2 Hz, we get into load shedding and low frequency trips, where generators are automatically disconnected to protect the system. This specification is set out in grid code, specifically balancing code 2 and operational code frequency limits, and that number is the cliff edge before we get widespread generator disconnection. Frequency is super important because a lot of machines and electronics rely on a stable 50 Hz signal, as it's what they were designed for, and straying too far from that can quickly damage them. To manage all of this, the NESO keeps different types of reserves ready to go, like backup power and load reduction tools. These reserves come in several layers depending on how quickly they need to act. First, there's primary frequency response, which kicks in within seconds. This uses fast acting generation like gas turbines, hydropower and increasingly batteries, which can inject power almost instantly. Some wind farms can also help by ramping up curtailed generation if needed. And if that's not enough, secondary frequency response follows, adjusting generation or load within about 30 seconds. If the system still needs help, NESO calls on fast reserves, bigger backup sources or load reduction that can activate within 2 minutes. And finally, if necessary, NESO relies on demand turndown, agreements where large users like factories voluntarily shut off to help balance the grid. This takes a few more minutes, but it's a vital last line of defence. The entire reserve system is designed around what's called the largest credible loss, the sudden failure of the biggest single generator or interconnector, while accounting for how much spinning mass or inertia is online to stabilise the grid. Normally this layered defence is enough to catch problems early, but sometimes these reserves can be overwhelmed, like during the UK blackout of 2019. In August 2019, a rare chain of events struck the UK grid. A lightning strike hit a high voltage line between Eton-Soken and Wymondley. The fault was cleared within milliseconds, as the grid is designed to do, but the resultant voltage disturbance rippled across the system. At that same moment, vulnerabilities at two major generators were exposed. First, at the Hornsea 1 offshore wind farm, a technical control fault caused around 737 megawatts of wind generation to disconnect. Almost simultaneously, at Little Barford gas-fired power station, the steam turbine tripped offline, followed shortly by one of the site's gas turbines, removing another 244 megawatts. Altogether, almost 1 gigawatt of generation vanished in moments. The sudden imbalance pulled the grid frequency down sharply. All fast responses activated, but the system had to absorb a total generation loss of 1,481 megawatts, pulling the frequency down to around 49.1 Hz, dangerously close to critical levels. Then, another turbine at Little Barford tripped, removing another 210 megawatts. This final shock pushed the frequency down to 48.8 Hz, the trigger point for automatic load shedding, That's when the Low Frequency Demand Disconnect Scheme, or LFDD, activated. LFDD is a last resort protection where the system automatically sheds parts of the national demand to prevent total collapse. It operates in stages, with each stage set to activate if frequency keeps dropping. Each stage typically disconnects 5 to 10% of national demand, up to a total potential of about 60% if needed. So in 2019, only the first stage was needed, cutting about 5% of national demand and affecting 1.1 million customers. Thanks to LFDD acting fast, the grid frequency stopped falling and began recovering. Within 5 minutes, frequency returned to a stable level of near 50 Hz, and over the next 40 minutes almost all customers were reconnected. It's not just how low the frequency gets that matters though, it's how fast it's changing, and that's where another protection setting comes in, RoCoF, or rate of change of frequency. If the frequency begins to drop too quickly, say faster than 1 Hz per second, RoCoF Protection can kick in to disconnect sensitive generators or prevent new ones from connecting, to avoid instability or damage. This is especially important for renewables and inverter-based systems, which don't tolerate fast frequency swings like big spinning turbines do. The faster the RoCoF, the less time operators have to respond, which is why inertia from synchronous machines is still so valuable. It slows the rate of change and buys critical seconds for other responses to kick in. Some systems also include under voltage load shedding, or UVLS, as well as voltage phase angle protection, but in the UK, frequency and RoCoF are the main drivers for protection actions in a large-scale disturbance. What happened in 2019 was a partial failure where the system protections worked. But if even more generation had been lost, or if protection had acted too late, we could have faced a full national blackout. This is where Black Start procedure comes in, an emergency plan to literally reboot the grid, piece by piece, and it's public on the NESO website, and aims to reconnect 60% of demand within 24 hours, and is defined as the procedure to recover from a partial or total shutdown of the National Electricity Transmission System, or NETS. In order to recover from a failure of the system, we need Black Start service providers, which are generators which meet a certain set of criteria to kickstart the grid. The Black Start service provider, or combination of providers, can start up following a total or partial shutdown, independent of external supplies. They need to be able to energise part of the network, and be able to provide block loading of local demand. So put simply, this means a generator must be able to start without needing power from the grid, and be able to meet the demand of its local area when connected to the grid. Power stations and substations actually test their Black Start capabilities each year to make sure they're prepared if the worst was ever to happen. Sometimes it doesn't go to plan though, so it's important to have plenty of backup options. So what sort of generation can we use to Black Start the grid? Well, if we look at the top requirement of Black Start providers, we have a very specific point on Black Starting the grid. The provider must be able to cold start with no grid connection in order to be relied upon as a Black Start provider, so nuclear is out of the question, because it takes a load of power and ramp up time to get going. But you might be thinking, well, they're usually on, providing a nice stable base load constantly. And you're right. If a blackout happens, they'll likely keep running without much issue, and the backup generators will just make sure the pumps keep running. But they can't typically cold start without the grid, so don't count. It will, however, be used to great effect during the restoration by providing lots of good stable frequency and power, acting as an anchor, if it remains connected to its own little energy island in the grid. In reality though, once the grid is lost and the diesels kick in, the reactors will likely be scrammed and shut down for safety, unless there's a special circumstance to risk it.
3.6. Not great, not terrible.
And providing the local demand is stable for it to supply. So with nuclear out, what about wind? Well, wind turbines and solar farms normally need power from the grid to operate the control systems and inverters. Without a stable grid signal, they can't synchronise and connect properly. However, modern offshore wind farms, like Dogger Bank, are starting to use advanced grid forming technology. Solar farms, on the other hand, almost always require an external grid signal to operate. Very few solar sites today have grid forming capability, although that's slowly changing with new inverter designs. Grid forming is becoming essential because historically the stability of the grid came from the spinning mass or inertia of big coal and gas turbines. As these older synchronous machines retire, we need renewables to help stabilise frequency changes by rapidly responding. New grid forming wind, battery and some solar systems can simulate this inertia electronically, known as synthetic inertia, helping to keep the grid steady during disturbances. So what other sorts of generation can we use now nuclear is eliminated? What about hydro and gas? Well, hydro's perfect, provided the reservoirs for pumped hydro are full, as they act like a big battery. Open the gates, rotate the turbines and you have a nice stable power for the local grid. However, England only has a few tens of megawatts of hydro compared to the mountains of Scotland and Wales, which are blessed with hydro generation of up 2.2 gigawatts in Wales. Of that, around 100 megawatts is natural and 2 gigawatts is pumped, and in Scotland roughly 2 gigawatts total, with 1.2 gigawatts of natural and around 700 megawatts of pumped. This gives a total UK hydro capacity of around 4.2 gigawatts, like the Tunnel Valley scheme in Scotland, where 90% of the natural hydro is. That's constant and depends on river flow and rainfall, whereas the remaining 2.8 gigawatts is pumped hydro like the Norwig and Festiniog in Wales, and Cruachan and Foyers in Scotland. So what about gas? Well, there's two types of gas turbine in use, and those are open cycle gas turbine and closed cycle gas turbine. Open cycle operates like a jet engine, where you burn fuel to turn the turbine, so it takes very little energy to start, whereas closed cycle use an additional steam turbine, which is a lot more sensitive to start up. A lot of modern CCGTs can run in open mode for black start flexibility, using a diesel generator to start. So to round that out, hydro, battery, open cycle gas turbine and some newer solar and wind can all be used to black start. So how does the black start happen? Well, these selected sites will be instructed to start generating power, and National Grid engineers will be sent to the substations they connect to for any manual switching to reconfigure the network and to monitor the situation, while the Transmission Network Control Centre, or TNCC, and NESO monitor and instruct remotely, while coordinating with the Distribution Network Operators, or DNOs, to gradually connect load and to ensure the system remains stable as little islands of electricity form. The UK is divided up into black start zones, defined in the NESO strategy, with each zone having its own black start providers, engineers and control strategies to restart independently if needed. Once we have these little energy islands online, we can gradually expand them, adding more demand and generation that requires the grid to start, such as the closed cycle gas turbines, the wind and solar that needed a reference or some input. Eventually these islands in each region connect up, much like the early grid, until we reform a synchronised single national grid. As we mentioned earlier, the NESO aims to get 60% of the network back online within 24 hours, so first it builds out the stable skeleton network to get there, but it's predicted that it might not get back to 100% until after a few days to a week. It all depends on what happens and the impact. For example, cables and overhead lines and substations destroyed in an attack could take weeks to temporarily fix and months to fully replace. What about interconnectors? Can we use all these links we have to other countries to restart things? Well, sadly not right now. Once the grid goes down, the interconnectors shut off, as they need to be stable on both sides to be online. However, because HVDC links are set up to produce 50 Hz on the UK side, we could connect the HVDC into an early island for a black start assist. But the NSO would be pretty hesitant to rely on this, as they can't control the other end, and it could bring the island down again if relied upon. Before we wrap up, let's zoom out. What happens when other countries face a black start? If you've enjoyed this video so far, remember to like and subscribe and leave a comment below on what you think we could do to make the system more stable. So depending on the energy mix and grid structure, the story looks very different, and it's a useful comparison to understand how vulnerable or resilient we really are. Take Spain for example, which was just in the news for a full grid collapse. It's heavily reliant on renewables like solar and wind, which aren't typically grid forming. That means it depends heavily on hydro, gas and batteries to recover from a blackout. The good news? Spain still has around 20 gigawatts of hydro and 30 gigawatts of gas, which provide dispatchable power, but its battery storage was only about 60 megawatts at the time, far too small to stabilise the system during the event. In response, the EU approved a €699 million state aid scheme in 2025 to boost battery capacity to as much as 3.5 gigawatts, which could make the difference in preventing future blackouts. France, which was also affected by the blackout, is a unique case, because between 40 and 60% of its electricity comes from nuclear, and while nuclear plants usually scram during a blackout, some are capable of operating in island mode, meaning they can keep powering their own systems or nearby load, ready to reconnect once the grid is stable. France also has around 25 gigawatts of hydro and 15 gigawatts of fossil generation to support Black Start, plus around 23 gigawatts each of wind and solar, and because it's so well connected to the other European grids, interconnectors often play a key role in restarting parts of the French system, assuming the neighbours aren't down too. For our US viewers, the story is quite different. The US doesn't have one national grid, instead it's made up of three major interconnections: the Eastern, Western and Texas grids, each with its own Black Start capabilities. In 2021, Texas, managed mostly by ERCOT, saw a catastrophic blackout affecting 4.5 million people, partly because it's isolated from the other two grids, limiting its ability to import electricity in a crisis. For the 5% of you watching from Deutschland, Germany offers another interesting contrast. It has over 66 gigawatts of wind, 67 gigawatts of solar, and around 4 to 5 gigawatts of battery storage, making it one of the most renewable heavy systems in the world. But, unlike Spain, Germany has maintained more grid forming capability, thanks to CHP plants, biomass and grid supportive coal and gas reserves. It also benefits from dense interconnection with its neighbours, allowing regional Black Start flexibility. And finally, the 5% of you watching from down under, Australia faces challenges similar to the UK: long distances, high solar and wind penetration, and pockets of low inertia. But it's been a leader in grid forming inverters, especially in South Australia, which has experienced near total separation before. Australia uses a mix of diesel, hydro and gas turbines, and increasingly large-scale batteries, like Hornsdale, to support fast response and Black Start services. So now you know what a Black Start is, how the grid sheds load, and why and how we go about restarting the grid if it falls down. You might have learned a few things about generation or grid code, and how this amazing system runs and how fragile it can be at times. I'll be exploring the two cases of partial grid shutdown mentioned in another video, as well as other more recent incidents, like Heathrow when the report is produced. Thanks for subscribing, and check out another one of my videos here.
The government will help. The government cannot help itself, let alone you.